So we're going to work with capacitors in parallel, in series, and then get to the point where we have them in the same circuit, parallel and series combinations. And so we're going to start with capacitors in parallel. And the thing we need to remember with capacitors in parallel are these three facts. If we have a combination in parallel, and again, the way to think about how we know they're in parallel is if you imagine charge flowing through our battery, it hits this point, and then it's going to split off into these different channels. And so if we think about it, right, the positive sides of each capacitor are on the same side of the battery. All the negative sides of the capacitor are on the opposite side. And so if we look here, our capacitors are in the parallel combination. And so the first thing we want to know is that when potential difference V is applied across several capacitors in parallel, the potential difference across each capacitor is the same. And the reason for that is just imagine that we got rid of these last two capacitors. Well, the potential across Q3 here, or C3, is that of the battery. Well, what if we got rid of C3 and C1? Well, the potential across C2 would have to be that of the battery. And if we got rid of C3 and C2, well, then again, the potential across C1 has to be that of the battery. And so if we put them all together, the same potential has to be there. The second thing we need to know is that when we finally find the equivalent capacitance, right? And so what that means is I could take these three capacitors, I could make a circuit that is simply made of one of these capacitors. And this equivalent capacitor is equal to the sum of C1 plus C2 plus C3 in this case. So it's the sum of all three of those. And because of that, that means that the total charge Q stored on this capacitor is the sum of the charge on Q1 plus Q2, which is the charge on C2 plus Q3. And so when they're in parallel, we're going to add the values of the capacitance to find the equivalent capacitors. The voltage across each capacitor when they are in parallel is the same. And the sum of the charges will add up to the total charge of the system. So that's capacitors in parallel. And so let's look at an example of that. And so here we have, again, a circuit. We have our battery here that has potential of 10 volts. We have C2 and C1, and obviously this is in a parallel combination. And they don't necessarily have to be parallel to each other. And so if I wanted to draw something like this comes up over here. What I drew here and this circuit up here are exactly the same capacitors, or the combination of capacitors, right? Here's C2, here's C1. Again, if we imagine charge flowing, right, the positive plates here, or the negative plates in this case, are on the same side of each other. So again, we're going to work our way forward to work our way backwards. So we're going to find the equivalent capacitance. And so we're going to eventually draw our circuit so that it has just one capacitor. So this is C equivalent. Well, we just know from the previous slide that the equivalent capacitance for capacitors in parallel is equal to the sum of the capacitors. And so we're going to add C1 and C2, and we'll get 25 microfarads. All right, and so if I wanted to, we could replace this two capacitor circuit with one capacitor that is 25 microfarads. For B, we're going to use the fact that Q equals CV, And I'm going to use my answer from A, so 25 microfarads times the voltage is 10 volts, and we get 250 microcoulombs. And so the total charge stored in this capacitor is 250 microcoulombs, which means the total charge stored in C1 plus the total charge stored in C2 is this 250 microcoulombs. C. We're going to find the potential across each capacitor. And so, again, since we're in parallel, I know the voltage from this point to this point has to be the same. And the reason for, like if you imagine this being plus 10 and this side being 0, well, I need the same potential drop across each of these to get that. And so V across C1 equals V across C2, which is going to be 10 volts. And finally, for the total charge, well, now that we know the potential across each capacitor, we're going to use our Q equals CV to find the total charge on Q1. So Q1 is C1 times the potential across it, which is 10. And so C1 is 20 microfarads times 10 volts. And so we get 200 microcoulombs, which means Q2 we already know has to be 50 since Q1 plus Q2 has to add up to my Q equivalent. And so we'll get that when we do the calculation as well. C2 times 10, and so that's 5 microfarads times 10 volts, and we get 50 microcoulombs. And so again, Q1 plus Q2 gives me the 250 microcoulombs total charge. The equivalent capacitance is 25 microfarads, and the voltage across each of those capacitors is 10 volts. And so that's a simple parallel combination of capacitors.